18. In the given question, we have to tell about the number of elastic constant in linear stress strain relationship for a 3D orthotropic material. Before going to answer the orthotropic material, let's, as we already know, but let's again understand isotropic material. Isotropic material are those material in which the properties, thermal, mechanical properties, is same in all the direction. For example, if this is an isotropic material, let's say same dimension, let's say L, and this is also L, or say it's a cuboid, and this is also L. Now this material, if it is subjected to some stress or force, let's say this is Y and this is X, then what will happen? For example, first it is subjected to the force in X direction. It will elongate in X direction, and there is a reduction in the dimension in the transverse. Here the length will increase plus, let's say, del L, and there is a reduction let's say del Y. Now if the same material is subjected to the force in the Y direction, it will elongate in the Y direction, and there is a reduction in the transverse direction to the applied force. This reduction, let's say del X, here also del X, and the change in length, this L plus del L. In the both case, if the material is isotropic, then del X will be equal to del Y, and the total change in the Y direction because of the same force. If sigma X is equal to sigma Y, then due to in X direction and Y direction, this will be same. It means the strain, that is the change in dimension to the original dimension, will remain same in all direction, in X direction and Y direction, if the force applied is same and the dimension is same. But this is the property of isotropic material. Now coming back to the question, orthotropic material. If in the case of the orthotropic material, the properties in the different direction is not same as like isotropic material. This is the properties are same, but in orthotropic material it is not same. For example, this is Y coordinate, this is X, and this is Z. If we are applying the force same 10 Newton, let's say, and the dimension are same, L, and this is also L, and this is also L, we will get elongation in the X direction, let's say del X. If now we apply the force in the material in Y direction, same force 10 Newton, we will get a deformation or the elongation del Y in Y direction. Similarly, in the Z direction, if we apply, then del X will not be equal to del Y, will not be equal to del Z. So the material property, like Young modulus Ex in the x direction is not equal to Ey and also not equal to Ez. And also in the orthotropic material, for example, if we are applying the shear force, let's say Fs, the deformation, angular deformation due to the force in x direction, gamma x, y, let's say gamma yz and gamma zx. These are the angular deformation when we apply the force parallel to the x coordinate or the x direction. We will get this angular deformation. Now if we apply the force, shear force in the y direction, let's say this, then the deformation we will get this. Similarly in the z direction we will get this angular deformation, but these will not be equal to same. By applying the same amount of force Fs, here also Fs, but we will get a different angular deformation. It means that the shear modulus in the xy direction, yz direction and zz direction will not be equal. And also the Poisson's ratio xy, by using these we can find the Poisson's ratio also. Poisson's ratio will not be same. So the final thing, we have to tell the number of independent elastic constant in the case of the orthotropic material. Here we know that Ex is not equal to Ey, not equal to Ez. Similarly, Poisson's ratio is also not same, and the shear modulus will also not be the same for a 3D orthotropic material. So the number of independent elastic constant are total 9. In the case of isotropic material, there are 2. Question number 19. The compatibility condition in theory of elasticity ensures that these strain, 6 strain component, these are the normal strain and these are the shear strain. This 6 strain equation is derived by using the compatibility equation, by assuming only that the body is deformable and there are no voids. Similarly to our continuum hypothesis used in fluid mechanics, that there are no voids, the medium is continuous. Similarly here also. So U, V and W are the displacement at any point in the material. As we suppose that the body remains continuous during the deformation, when we are applying force, there is deformations exist. So it follows that each component of displacement U, V, W must be continuous at any point. So if these are the continuous, then a single valued function exists only at that point. Hence the displacement are single valued and continuous. This will be the right answer. The option C is correct. Question number 20. In a spring mass damper single degree of freedom system, we can make one single degree of freedom system the simple in the given question the mass is m equal to 2 kg and undamped natural frequency is given. Undamped, it is not damped, so frequency is given 20 hertz for the natural frequency Fn. We have to find the critical damping constant of the system, which is denoted by Cc, and the critical damping constant of the system Cc is having the formula 2m omega n. It is the natural frequency in radian per second. We know that omega n is k by m. For a spring mass system, and also omega n, we know that 2 pi Fn. 2 pi into 20, we will get 40 pi radian per second. This is the natural frequency in radian per second. We have to find the critical damping of the system. By putting these values, mass and omega n, in this equation, we will get the answer. Cc equal to 2, mass is given 2 kg, omega n is 40 pi. We will get 160 pi Newton second per meter. This is the unit for the viscous dampers used in the system. Why critical damping? What is the importance? For example, this is the cantilever beam and this is its mean position. Now we are giving some disturbance. It will deflect like this, and now we are leaving. It will, after some time, it will definitely overshoot its mean position and deflect like this. So any point, for example this point, upper fiber of the beam will be under compression when the beam is upside at this position A. Now if the beam is downside, in this deflected position, then the same point will be under tension. So the beam will be under a cyclic loading. When it is upside, this point will be under compression. When it is deflected downward, then this point will be under tension. So there is a cyclic loading. This loading may cause the beam to undergo any fatigue, which we don't want for any structure, because most of the structure fails because of the fatigue. So in order to prevent this, we can use some damper, critically damped system, so that if we are deflecting the beam by some force and we are leaving, then the system or the beam will directly come back to its mean position without overshooting the mean position. Question number 63. A parallelogram is given which is subjected to stresses sigma 1 and sigma 2 angle theta. The length of these edges are A and B. We have to find which state of stress the plate are in equilibrium. For that, we have to take the moment. We are simply dividing it in the 4 parts, and we are taking the moment about center point. We will get sigma 1 into A, multiplied by b by 2. This is a force and this is the perpendicular distance, minus sigma 2 b into a by 2 cos theta equal to 0. By solving this, you will get sigma 1 equal to sigma 2. Question number 64. A column of solid circular cross section and L is the length with various end conditions. We have to choose which one is right with the corresponding effective length for the buckling. We know that the buckling load is pi square EI upon LE, effective length square. This formula is known as Euler buckling load or Euler buckling formula, in which E is the modulus of elasticity of that column and I is the second moment of area of the cross section of that column. L is the effective length of that column. So for the different boundary conditions, for example, if the column is fixed and fixed ended, if this is the length L, then the effective length is L by 2. And if the boundary condition is hinge and fixed, here it is hinged at one end and fixed at another end. If the length is L, then effective length is L by root 2 approximately. Now, if the boundary condition of that column is fixed and another end is free, then the effective length is 2L. If the boundary condition of that column is hinged from both the ends, then effective length is equal to L. From the given options, option A is correct. Question number 65. A thin wall tube radius of R and has a central web which divides it into two symmetrical cells. A torque M is acting on the section. We have to find the shear flow in the central web. The section is given like this. Mean radius is R. We have to find the shear flow at the central web. What is the shear flow in this web? Well, the answer is 0. Why the shear flow in this central web is 0? For understanding, we are going to assume some numerical values instead of solving it parametric form, in the form of the parametric or some variables. We'll get the shear flow in this central web is 0. As the question stated that central web is dividing this section into two symmetrical, means half section area 1 of this closed section will be same equal to this cell. We are saying this is equal to A, and let's assume the thickness is uniform T, subjected by a torque T. We know that the torque for a thin walled closed section is given by this, where Q1 and Q2 are the shear flow in the section or the cells, cell 1 and cell 2. It is assumed that the rate of twist for the cell 1 will be equal to the cell 2 is equal to the rate of twist of the whole section due to the torsion. So we know that the formula for the rate of twist in case of thin walled closed section is given by 1 by 2 A G Q ds by T, where S is the parameter, T is the thickness, Q is the shear flow, A is the area of that closed section or the cell, G is the shear modulus. Now we are considering for the cell 1. Then 2, area is same. We are also assuming the shear modulus is same as nothing is given in the question. So for the cell 1, the shear flow in this outer ring is Q1. So Q1 into parameter, what will be the parameter? 2 pi r divided by 2, because we know that the parameter of this circle will be 2 pi r and half of that will be pi r, pi into r, and thickness is assumed to be T. And shear flow in this central web will be Q1 minus Q2, and this is the parameter, which is nothing but 2 into r divided by T. Q1 minus Q2. Why Q1 minus Q2? Because from the direction here, Q1 is going in this direction and Q2 is coming in this direction. So Q1 minus Q2 into 2r. Similarly, for the cell 2, 1 by 2 A G. Now Q2 in this ring, Q2 pi into r, same as the parameter, divided by T, plus again now we are considering this, then Q2 is coming in this direction and Q1 is going in this direction at the central web. So Q2 minus Q1, and same parameter is 2r, this is 2r divided by T. Now from this equation we are equating this and this. We will get, as we are equating this and this, then this and this is common, then we can eliminate this, then we will get, and also thickness is same here and here, then we will get Q pi r plus Q1 minus Q2 2r equal to Q2 pi r plus Q2 minus Q1 into 2r. So from here Q1 is pi r plus 2r minus Q2 into 2r. We are just solving this, and Q2 pi r plus 2r minus Q1 2r. So we are taking this here, Q1 pi r plus 2r minus 2r, we will get Q2 pi r plus 2r. We are taking this here plus here plus 2r. These and these are the same, so this will eliminate and we will get Q1 equal to Q2. Okay, now we already know that Q1 is in this direction, means Q1 is flowing in this direction, and Q2 is also in the direction, so Q2 is also flowing in this direction, as Q1 equal to Q2. So the net shear flow in this, as these two are in opposite direction, so the net shear flow in the central web will be equal to 0. So this is the reason why the B answer is correct. Question number 66. It is a simple problem, as we all know how to solve the bending moment shear force diagrams. And this is hinge and this is roller and this is moment at L by 2 and L by 2. This is the axis. Here we have to find the shear force diagram. Let's say A, C and B. First, we have to remember we have to find a shear force diagram. As in the option, their bending moment diagram is also given, so don't go for the bending moment. You have to know what is asked in the question. Here shear force is asked. So we know that RA, let's RA be the reaction at the support A and RB at the support B point. We know that the hinge will support two reactions, RH horizontal reaction, as there is no force in the horizontal direction, so the RH will be equal to 0. We have to solve it by using the equation for the static equilibrium. The static equilibrium equation are summation of a force in the vertical direction is 0, summation of the force in the horizontal direction is 0, and similarly summation of moment at any point for a statically stable system is 0, either mx or either my or mz. Okay, as a hinge cannot react to any moment, so first we have to find the reactions and the supports. We are using summation of forces in the vertical direction is 0. So total force RA we are considering, let's say, positive side or the direction of the force in the positive y-axis is positive and downward is negative. We know that there we assume two forces RA and RB are in positive direction. RB, there are no other force acting, so equal to 0. Now we have to use another equation of static equilibrium. Moment is equal to 0 at any point. So we are using, let's say, moment, we are taking the moment about point A equal to 0. Now we are taking convention like positive is clockwise and anti-clockwise is negative. Okay. So the moment, we know that the moment is nothing but force into perpendicular distance. Now we are taking the moment about point A. As the moment about point A will be 0. Why? Because we know that the support at the point A is hinge, and hinge does not resist any moment. So the moment about point A will be 0. Moment, we know that the moment is the force multiplied by perpendicular distance. Here RB is the force. So RB acting in such a way that produce the moment anti-clockwise about the point A. So minus RB multiplied by L, which is the length, and the moment at point C is clockwise, as there is no other force between B and C. So moment at point C is clockwise, so we are taking positive. and the force Ra, reactive force at Ra does not produce the moment above itself because there is no perpendicular distance. So Rb, the reaction we will get at this support. From our first equation that we solved by using the summation of vertical forces is equal to 0, we will get the Ra reactive force at the support A is minus m by L. Now we have to draw the shear force diagram. At point A, there is the shear force minus m by L. Let this is negative, this is positive, and there are no any other force acting between the A, B and C, A, C and also B. There is movement but does not affect the shear force diagram. So there are no point load, no distributed load, so the moment, the shear force will remain constant up to the point B. Just at the point B, there is force Rb, m by L. So the shear force diagram will goes to 0. So this will be the correct answer, as the answer is C is the correct answer, m by L. Before solving the question number 67, first we have to understand what is idealization and why do we do this idealization. For example, this is a wing structure, a cross-sectional area is shown here. For example, this is the front spar, this is the main spar, and this is the rear spar, and these are some stiffeners located. Why do we idealization? For example, if this kind of structure is given to you and you have to solve this by hand calculation, this will be very difficult to solve. So in order to analyze the section of this type would be complicated and tedious unless we are doing some idealization or simplification. So to give a fast result for our preliminary investigation, simplification and idealization have the great importance. So what we do, instead of solving the stresses on these stiffeners, we combine this area of this stiffeners and we call them as a boom. So for example, if this section is subjected to bending moment, and we have done the questions based on if this stiffener is subjected to bending, we can find the stresses at each and every point. But compared to this whole section, the area of these sections are very compared to this whole section. So what we do, instead of calculating the stresses at each and every point, if the wing is subjected to the movement, then we collapse this area or merge them and form a structure we call this boom. Instead of solving these point by point stresses, we are solving the stress at this location with having some area A. So this will reduce our calculation time. So this type of complex structure may be idealized into simpler mechanical models which behave very nearly to the same as actual under the given loading condition. Now coming back to the question, this section is given. These are the idealized structure having the area A, and the small one is 0.1 centimeter square of area, and this is the z-axis and this is the y-axis, and the moment applied is my. We know the formula of bending moment, m by I equal to sigma upon y equal to E by R. So as a sigma equal to m by y upon I. The coordinate system is given. This is y, this is z, and this is x. So because of the bending, there will be stress, normal stress along the x direction. That would be equal to sigma x equal to m by I multiplied by z. We have to find the stress in the top boom to the bottom boom. So the distance from the y-axis to these top booms are 2 cm. Sigma x for the top equal to my by I into 2. Similarly, normal stress because of bending in the bottom booms will be equal to my by I, as the distance from the y-axis to the bottom boom is 2. As the moment is the same and moment of inertia about the y-axis will be same, it will be equal to sigma area of the boom, which is denoted by B, into z square. Z is the distance from the y-axis. This will be same. It is like a constant for the section, and my is also given, which is constant. So sigma at the top boom and the bottom will be equal to 1. Why? Because sigma is directly proportional to z from here. This is the constant, so this sigma is proportional to z, and z for the top boom is 2 cm and bottom boom is also 2 cm. So sigma x top by sigma x bottom will be equal to 2 by 2, because m by divided by I is common or constant. If we are multiplying, then this will eliminate itself. So the answer is 1. In the question number 68, an engineer is asked to test a system which can be idealized as single degree of freedom with viscous damping. Viscous damping is given in the system. The frequency response test was conducted. It was found that the quality factor, which is denoted by Q, is given equal to 10. We have to find the logarithmic decrement if the free vibration test is performed. Logarithmic decrement is denoted by delta. Logarithmic decrement is equal to 2 by E, this is the formula, 1 minus E square. And also there is one more formula, delta equal to 1 by M ln log x 1 upon xn plus 1. So the quality factor is given. The quality factor having the formula 1 by 2E. What is E? E is the damping ratio. Damping ratio. What is damping ratio? Actually, damping ratio is the ratio of the damping present in the system to the critical damping. Okay. So we can find the E 1 by 2Q, and damping ratio is 2 multiply quality factor is given by, which is 10, then we will get 1 by 20, which is equal to 0.05. As the damping ratio is less than 1, it means the system is underdamped. It means if the system is disturbed from its mean position, for example, this is the mean position, if disturbed from here to here and release, then it will show oscillation before coming to the rest. If E is less than 1, we call them underdamped system. So now we have to find the logarithmic decrement. We found that E equal to 0.05. Then if we put the value of E in the formula of logarithmic decrement is 2 pi E 1 minus E square, we will get the answer pi by 10. C option is correct. We will get the answer this. Question number 71, 72 and 73. In the given question, there is a two-dimensional stress state is given. In order to find the principal stress, and also failure stress is given 350 MPa megapascal. In 71 question, the principal stress sigma 1 and sigma 2 need to be found at any plane under the complex loading, for example sigma x, sigma y, and also shear stress is given, and sigma z. Then we will get the sigma 1, sigma 2 and sigma 3 normal stresses, which are the maximum on some plane. In the case of the two-dimensional state of stress, sigma 3 is 0. Now in the question, state of stress is given minus 8c, 5c, 5c, 16c. In order to find the principal stresses, as we know how to solve characteristic equation, or lambda 5c 16c minus lambda, similar to the matrix. Now we have to find the value of the lambda. After solving for the lambda, we will get the value 17c and 9 minus 9c. The values of these lambda are the principal stresses. In the question 72, question number 72, we have to find the maximum shear stress. We all know the maximum shear stress formula is sigma 1 minus sigma 2 divided by 2 for a two-dimensional state of stress. Here 17 minus 9 plus c divided by 2. We will get the answer 13c. Option C is correct, megapascal. In the question number 17, the maximum value of the C for the safe loading of the structure based on von Mises failure criteria is to be found. Von Mises criteria is mainly used for the ductile material, and we know that for the two-dimensional state of stress in which the principal stress in the third direction is 0, then we will get the formula sigma 1 square plus sigma 2 square minus sigma 1 multiplied sigma 2 less than equal to sigma f square, where the sigma f is the failure stress which is given 350 megapascal, and sigma 1 and sigma 2 and sigma 3 are the principal stresses. Now we already calculated the value of the sigma 1 and sigma 2, which is nothing but 17 C megapascal, sigma 2 is minus 9 C megapascal, and the failure stress is already given in the question. Now we have to put these value into this equation. We will get, now we are putting 17 C square whole square. We are taking common C square from the equation and equal to sigma f square. After solving this equation, we will get 234.225. Taking square root, we will get 15.3. Option B is the correct answer. Question number 84. An idealized thin-walled two-cell symmetrical box is shown in the figure where the shear force in the y direction is given 480 Newton and the shear force in the z direction is given 300 Newton, and a torque M is also acting at the shear center. In the question number 84, we have to find the shear flow Q1 and the Q2. This is the idealized section. For solving the question, we have to understand, or we have to know, the property of a constant shear flow section. Before solving this question, we have to know the property of constant shear flow in the section. For example, if this and this are the boom, idealized section, and the shear flow is Q1, 2, and the coordinate of these booms are, let's say, x1, y1 and x2, y2. Then if we want to find the force in x direction and y direction, then the force in the x direction will be equal to Q12, the distance between these two booms in the x direction, or the x coordinate, x2 minus x1. Similarly, if we want to calculate the force due to this constant shear flow, it is not changing with the distance. So Fy is the force in the y direction is Q12, and the coordinate of this boom y2 minus y1. Now for calculating the shear flow Q1 and Q2, we have to use this property. Q2 and Q1 are the constant shear flow in this thin wall. Now we will use the property shear force in the y direction is 480 Newton. Shear flow is nothing but is the shear force per unit distance or per unit length. We know that Vy is equal to 480 Newton acting in z direction, and the shear flow which is acting in the z direction is to be multiplied by their distance, or the that wall on which they are acting. So that summation will be equal to 480 Newton. 480 equal to will be this 22 multiplied by 12, and also it is acting in the same direction, plus 22 multiplied by 12. Now this shear flow is acting opposite to the y direction, minus 2 multiplied by 12, this is 12, and Q1 is acting in this direction. We are taking this direction to be positive, plus Q1 into 12. These 12 are common, 480 to 12, 22 plus 22 minus 2 plus Q1. By solving this equation and simplifying it, we will get this. Now we can find the Q1 is equal to minus 2 Newton per centimeter. In the z direction, 300 Newton is given. Z direction is upward. So the force will be equal to 10 multiply this shear flow, and this wall distance is 10 is given here, plus we are taking positive in the upward direction, Q2 multiply the distance 10, and this is opposite direction, so minus 2 into 10, and there are no other forces. So 100 plus 10 Q2 minus 20. We can find the Q2, 200, we will get 22 Newton per centimeter. So we get the Q1 equal to minus 2 Newton per centimeter, and Q2 is this. So option A is the correct answer. Question number 85, we have to find the torque. Torque is nothing but, we know that force multiplied by perpendicular distance, and in the question it is stated that shear force Vy and the Vz, also the torque, all are acting at the shear center. As the section is symmetrical, and shear center will be at the center. So in order to find the torque, we know that if this is the shear flow Q in this section, then the shear force in this section will be F equal to Q into ds. If ds is the length, then the torque about the shear center or the center will be equal to Q into ds multiplied by this perpendicular distance, let's say x. In this way we are going to solve for the torque. So you know that we are taking positive and this is negative sign convention. So the moment at the shear center due to shear flow Q2 will be equal to 10 multiplied by distance 12 and 2 multiplied by 12 into 5 minus Q1, that is in the opposite direction, Q1 multiplied by the distance 12 and the perpendicular distance 5. Similarly, 2 into 10 multiplied by 12 plus 22 at the bottom side into 12 into 5 plus 22 multiplied by 12 into 5. Shear flow in this web will not produce any movement about this point or the shear center. As Q2 we know that 22 Newton centimeter, and Q1 as we calculated minus 2 Newton per centimeter. After putting these value into this Q2 and the Q1, we will get the moment. These all will be equal to the moment M. We will get the moment of 5760.0 Newton centimeter. The option B will be the correct answer.